What's up? What's up? It's your man Jimmy Chan. All right, so we're talking about mathematical models here. So essentially, it's just a bunch of example problems that we're going to do that is going to involve some kind of perimeter, area, distance formula. It could also be the Pythagorean theorem, which is a squared plus b squared equals c squared. So it's a bunch of old formulas that you've learned in the past that's coming back to haunt you. Except over here, there should be a plus right there. All right, so that is very important, plus right there. All right, so let's take a look at the very first problem here. So let p of x comma y, let p x comma y be a point on the graph of y equals x squared minus 4. So this red line right here is x squared minus 4, and here's a point. Okay, express the distance d from p to the origin. So in other words, if this point P moves, right, clearly my distance is going to be different. It's going to be very long here, very short here. It's going to get longer, and then it's going to get shorter again, and it's going to get longer again, right? So we're just placing that P right there. Excuse me. So I am looking for distance. So distance formula says that d squared is equal to x2 minus x1 squared plus y2 minus y1 squared. Okay, so I know the origin is 0, 0. So let's place those in there. So let me go ahead and duplicate this right here. Right, and let's replace the x and y to be 0, and I'm going to do it for these ones just so that I don't have to deal with negative numbers. 0 and 0. Okay, the question is, how am I going to enter this point here, because this point is going to be different depending on where I'm going, right? So it's not going to be an actual number, right? And I don't want to just use x and y, because then I'm not really finding distance as in terms of x, right? Because I don't want 3 variables, okay? However, if I put an x value in here, I'm going to get a y value. X value in here, I'll get a y value, right? So that tells me that, so let me do this here. Let me go ahead and put this in blue, okay? So that tells me, oops, I don't want that y in there. Duplicate, there we go. So if I put an x value in here, I'm going to get y value. But if I put an x, what am I doing with that x? What am I really doing with that x? I'm going to take the x, I'm going to square it, and then subtract 4. Is that right? Right? So here is the thing. What's going to happen, is that this parentheses here is just going to be left x, because x minus 0 is just x squared. The second parentheses, x squared minus 4 minus 0, is also just x squared minus 4 squared. So I'm going to have that right there. Okay? Now, the first one is easy. So I have d squared is equal to x squared. However, the second one, I'm going to have to go ahead and FOIL. So that's going to give me x to the 4th minus 8x squared plus 16. So let me combine like terms. So I have d squared is equal to x to the 4th minus 7x squared plus 16. So which means that I have d is going to equal to the square root of x to the 4th minus 7x squared plus 16. Okay. So that is what my actual formula for, oopsies, boop, for my distance. Now, here's the biggest part. Because I am essentially doing substitution, right? What's actually happening is this. I'm naming the distance in terms of x. So this is actually a distance function, okay? Now, what I can also do is, because obviously when I am doing this piece here as I'm trying to figure this out, I can go, okay, right there was the x value, and of course right here, the x value, I'm really not sure what the x value is, so I don't really know what the distance is going to be, right? I know what the y value is, but I don't know what the x value is. But the y value doesn't really help me in this equation. So what I can do is go ahead and graph this, right, as a function of distance. So when I graph that, it's actually going to turn out something like this. Hey. So now what I can do is, based on the so-called x value, I can see what the distance is. So remember when I said in the beginning, right? As I move this, it's going from long to short, a little bit longer to short, and then long again, right? So, as I was saying before, it's going from long, right? High distance. It's going to go down, then it's going to get longer, get shorter, and then go very long again. Okay? So that right there, I can call this d of x. And up here with the red line, that was called the f of x, or the y. Okay? So that is how we would solve for distance. All right? All right, so let's take a look at this. So it says a rectangle has a corner in quadrant 1 on the graph. On the graph, that is y equals 9 minus x squared. And at the origin, a third on the positive y-axis, and the fourth on the positive x-axis. So it's going to look something like this. All right, bring that up here so that you guys can see. So in other words, here, if I was to take this corner and change it along this green line, it's going to give me different area of that rectangle. Okay, so, and notice how it says the positive x-axis and the positive y-axis. So this can't actually come over on this side. Okay, so it's literally just staying on this side. Okay, so I gotta find this area. Okay, so again, this is my f of x, which is equal to 9 minus x squared. That's the green line. So to find the area, well, what's area? Area is equal to base times height, or length times width, right? Okay, so over here I have a base and a height. So base, I typically call it my x because it goes left and right. So guess what? It is my x value, right? So I can say that the area is equal to x times my y value, right? Because that's a height. But what is my y value? It all depends on which x I do, right? So if I was to plug this x in here, what am I going to get? What I would get is 9, well, actually, you know what? I would say x times y, which is really equal to the x times, and the y value is actually equal to 9 minus x squared. So it's actually not this dot anymore. It's actually going to be a parentheses. Okay? So with that being said, what I now have is that the area now became a function, and that's going to be a 9x minus x to the third. Okay? So that is my area. There we go. All right. Let's look at another example here. Okay. Oh, and again, of course, if I was to choose this point and I go, okay, I'm going to go over here and what's the area for that, right? And then I can go, okay, what's the area for this? And that is easy because I can see that the x value is 2, so I can throw it in to find the y value. But what if I had it right here? Better yet, what if I asked you, hey, based on this, what is my maximum area? You're gonna be like, well, let me calculate a bunch of them and let's see where it is, right? So that's where the problem is. So if we were to graph this, right? If we were to graph that, then what we're gonna have is this graph right here. So I guess I should change all of this to red since that was green, so I'll change this to red. Right, so it matches this red here on this side. So what we can do is when we graph it, this is the function we actually get. So look, it's an upside down, kind of like an upside down parabola, but this side of it actually is going to keep on going on. However, when you look at this, this is my maximum point, meaning, so my y-axis right now is really my area. Okay, so at the highest point, it would be my highest area, like my largest area, which you can see that the largest area I'm going to get is 10.392, right? Where is it? When x is equal to 1.732. Okay, is when I'm going to get the largest area. All right, so let's take a look at another example here. All right, so an island is 2 miles from the nearest point P. On a straight seashore, a town is 11 miles from the shore from P. Okay, so find the time it takes a person who can row a boat. So we're going to row a boat along this distance here, and then we're going to walk this 11 minus x at 4 miles an hour, right? And we want to see how much time it takes for us to do these two things right here, okay? So, if you remember, distance is equal to rate times time. And we're looking for time here, right? Because this asks me find the time it takes. So that means t is equal to the distance divided by the rate. All right, great. So if that's the case, we need to know what this distance is. We're not just going to use d because everything else is in x's, right, and numbers. So we need to find d. Oops, I move. Here's the island. There we go. The island is here, and then we got to get to the town. All right, so anyways, so I got to find d. Well, look at what I have here with the d. I have a right triangle. So to me, d squared is equal to, which is the hypotenuse, equals to a squared plus b squared, which is a Pythagorean theorem. So d squared is equal to 2 squared plus x squared. So d is going to equal to the square root of x squared plus 4, because x squared plus 2 squared is 4. Okay, so that's my distance. So as I'm rowing the boat here, in terms of x, I'm rowing this distance at 3 miles an hour. So the time for the boat is going to be the distance, which is the square root of divided by my 3 miles an hour. Okay. Then I have this walk right here, so that means I need the time for my walk right? What distance am I walking? I'm walking this distance here, x minus 11. And how fast am I walking this? I'm walking this at 4 miles an hour. So my total time, right? So time total is going to equal to this plus this. So that's the total amount of time that's going to take me to make these travels. And there we go. Now, if I was to graph this, so again, this total part that I just talked about, now since it's in terms of x, I can say this is t of x. Okay, so it's a time versus the distance, right? So I can talk about what distance he's gone and what time marker he should be at as we go. All right, one more. So what if we were given these things right here, right? So when we plot these, so to plot these on Desmos, again, you'll go in the graphing calculator, hit the plus sign, hit table. So let me go ahead and circle those, plus sign, the table. And you will start a table. And you'll enter all of these data. So here's my x value, here's my y value, type those in. And what it will do, it will graph all of those for you. Okay? So when you look at this, you can see that this is not very linear, right? It looks a little bit curved, right? So the next thing that we know that's curved would be a so-called quadratic. And with quadratic, we know that y is equal to ax squared plus bx plus c. Now, what do we notice here? What x values and what y values are we using? We're using x sub 1 and y sub 1. So what we have to do is make sure that we're going to put y sub 1 and x sub 1 squared and x sub 1 there. Okay, so this would be what we would put in, except we're not going to say it's equal. We're going to say it's approximate. Okay, so I have down here, I can get rid of this. However, let me bring this up and show you guys what you guys can see here. Let me see. There we go. Actually, this can probably go, let's see. All right, so if you look at this right now, so you can still see all the points I put in, and here is what I plugged in right here, okay? So you can see that where my A is, what my B is, and what my C is, and you can see exactly what I plugged in, exactly what I said right here, okay? So the equation that I have on this purple line is going to be y is equal to 0.015 x squared minus 1.022 x plus 27.6257. Okay, so this is actually the equation of what is close to going through all of these points. And if you look at the the r squared is 0.9972. So in other words, look at how almost perfect these are, right? It's very, very close. If anything, they're actually touching, right? Or going through the points. So this is a pretty darn good line for those points. All right. Well, I hope that helps. Any questions, let me know. See ya. Bye.